So we've been talking a lot about the derivative as a function, and I want to tie this back one more time to talking about slopes and instantaneous rate of change by going back and looking at graphs in GeoGebra again. So what we're going to do is we're going to see an example of where the derivative does exist and works out the way we expect it to. And we're going to look at two classic examples of where the derivative doesn't exist. That if we calculated the limit of the difference quotient, the limit would not exist. And we're going to see examples of how that doesn't work looking at graphs. All right, so let's pop over to GeoGebra right now. All right, so here's our classic example of x squared at the point 2 comma 4. And what we have talked about at this point is, I hope you recognize that the derivative of x squared is 2x. Whatever our x value is, if we multiply that by 2, that's going to be the value of the derivative. So at this point, 2 comma 4, if we zoom in really close, so 2 times 2 is 4. So we would expect to see that the derivative of this function is 4. That's what we would get when we calculate it. And what we can see is when we zoom in pretty closely and see this instantaneous rate of change, that this line is really close to a straight line that has a slope of up 4 over 1. So the slope is 4 over 1, just like the derivative is. All right, and if we came back out and calculated this not at 2 comma 4, but at 3 comma 9, all right, I got to move my graph a little bit. But again, if we move in here, we would expect to see a slope of 6. And once again, this is 1, 2, 3, 4, 5, 6 up and 1 over. So if this isn't exactly 1 over or 6 over 1, it's close enough for me. All right, let's take a look at two examples of where the derivative doesn't exist at a point. All right, so here is the graph of y is equal to the absolute value of x. And we're going to look at this at 0. Okay, so as I'm homing in on the origin, what we saw in the last example is that the more we zoomed in, the more that the graph looked like a straight line and we could calculate its slope. But the more and more we're zooming in on the origin here, this graph isn't changing a bit. There is nothing about this graph that is looking like a straight line at 0 whose slope we can calculate. All right, so we're going to say that that slope doesn't exist. The derivative at 0 does not exist. And if we calculated that difference quotient, we would see what the problem was, that that limit doesn't exist because on the left-hand side, the derivative from the negative side is -1. The derivative from the positive side is +1. And at 0, that left and right limit do not equal each other. So the two-sided limit does not exist at the origin. At any other point, though, if I zoomed in here, you can see that after a little bit of zooming in, this does look exactly like a straight line with a slope of 1. So the absolute value function is differentiable at every point except when x equals 0. And over here on this side, the derivative is equal to 1. Over here on this side, the derivative is equal to -1, which matches our intuition that the derivative of a line should be equal to the slope of the line wherever it is. All right, so here's an example. The absolute value of the function at x equals 0 does not exist because the left and right hand sides of that limit are not the same. Here's the other example I'll look at. This is the graph of y is equal to the cube root of x. All right, so when x is equal to 1, the cube root of 1 is 1. The cube root of 8 is 2 because 2 times 2 times 2 is equal to 8. All right, and so that's how that works. Once again, let's home in on the origin here and see what's happening when this line gets closer and closer to being a straight line. So at this point, I really can't tell the difference between this and a straight line. But what's the slope of this line? Well, this is a vertical line. So a vertical line has no slope. We might say it has infinite slope or negative infinite slope, depending on which way, whether you think that this line is increasing or decreasing. But the point is that we cannot calculate a slope here. And once again, we would see the same problem if we went and tried to calculate the derivative of this function when x is equal to 0 using the traditional methods we've used up to this point. We would find that we were taking the limit of some number over 0, and that limit's not going to exist because it grows without bound. All right, once again, this graph at any other point, let's home in when x is equal to 1 and see if we can tell what the slope of this function is. All right, so this looks like it's going up 1 and over 3. So this function is differentiable when x is equal to 1, and it has a derivative of 1/3. Okay? So that is what I wanted to talk about in this video, talking about examples of when functions aren't differentiable. So that's kind of important stuff. There's a third thing that's really important that I didn't mention in those two graphs, which is that a function needs to be continuous at a point in order to be differentiable. So if the x value, if the function goes like this and then jumps down here like this, we can't talk about the slope of the point when x is making that jump discontinuity, because it doesn't make any sense. Once again, that limit doesn't exist for continuity, and so we're not going to be able to calculate it. So those are the three main reasons why a function isn't going to be differentiable. Either it isn't continuous at the point, or it doesn't have the same derivative coming from the left-hand side as it does from the right-hand side, or the slope does have a limit, but it's positive or negative infinity. So those are the three reasons why a function would not be differentiable at a point. And going forward, we're going to talk more about the geometry and the graphing of these derivatives and how we can use those to solve interesting problems.